Welcome back, everyone. Last time we explored the strength of materials and how different substances hold under stress. But this week we're diving into circuits and electricity. Electricity is what powers our lights, computers, phones, and even some cars. Without it, we'd be sitting here in the dark. Before we start, quick question. Can you guys name a device in your house that needs electricity? What do you think would happen if electricity stopped flowing to it? Feel free to pause me and think about that. So what is electricity actually? Electricity is the movement of tiny particles called electrons. Think of electrons like tiny runners carrying energy through a wire. We can't see them directly, but we can see their effects. Lights turning on, fans spinning, and your phone charging. Electricity can come from batteries or from power plants. Batteries give us portable electricity, while power plants send electricity through wires to our homes. For electricity to flow, everything must be connected in a big ring. This is called a circuit. Circuit sounds complicated, but I guarantee you it's simpler than you think. A circuit is a complete path that electricity can travel through. If the path is broken, electricity stops flowing. Just like if a road is blocked, cars can't get through. We can call these open circuits and closed circuits. You can see an example of closed circuit at the top corner and one of an open circuit at the bottom corner. The one that's open on the bottom corner will not light the light bulb, even though it's painted yellow. In reality, this would not function well. And it's not just because the battery is vertical for whatever reason, but it's more so because the energy can't flow through. It has a cut. Where it's broken means it can't get to that other side, and therefore cannot flow. That may sound complicated, but maybe it's easier if I break it down into parts. Now, every circuit has three basic components. There's a power source, like a battery, a path, typically made of wires, and a load, something that uses electricity, like a light bulb or a motor. If any part is missing, the circuit won't work. For example, the lamp won't light if the plug isn't connected, or if it doesn't have a bulb screwed in. You might also notice there is a switch component. Although that one isn't necessary, it's incredibly common in circuits. For example, your ceiling fan has a switch, and though it's not in the shape of a button, instead it's strings that you pull down on. That is a type of switch, and again, it's not necessary for a circuit to work. But generally, circuits aren't seen without switches. To go a little bit more into depth about this, a switch is like a gate for electricity. And this simple idea is in everything from your light switches to your computer's power button. Now, electricity needs something to travel through. Materials that let electricity flow easily are called conductors. Metals like copper and aluminum are great examples. But then the materials that don't let electricity flow are insulators, like rubber, glass, or plastic. That's why wires are coated in plastic, to keep us safe from the electricity traveling inside. You can look beside you and see your phone charger, and it's covered in rubber, and if you touch it, it's not like you're getting charged, you don't feel a shock at all. But it's giving your phone electricity. It's because it's covered. The wires inside make it to where you're protected. Another example are those glass balls that you see electricity in, that when you put your hands close to it, it's almost like it's trying to touch you. But the electricity doesn't reach you and you can't actually feel anything because there's that glass in between protecting you. Now, before I move on, I want to emphasize that electricity is powerful and dangerous if it's not handled correctly. You should never touch electrical outlets or bare wires, never use damaged cords, and keep water away from electronics. Because believe it or not, water is a conductor, which means that it can send electricity through there. And then if you touch that water, you might get hurt. Electricity always takes the easiest path to the ground. And if you're touching something that gives it that path, it could pass through you. That's why we need to respect it. There's a series circuit where all parts are connected in one single path, which means that if one bulb goes out, the whole circuit stops working. And then there's a parallel circuit, where parts are connected on separate paths. If one bulb goes out, the other can still work. You can see the series circuit at the top corner and a parallel circuit on the bottom corner. Think of a series circuit like Christmas lights, where one broken bulb stops all the others. Parallel circuits are like the wiring in your house. Your bedroom light can be off, but the kitchen light still works. Now, we already went over the electrical current, how it's a flow of electrons through a circuit, but we didn't go very in depth into that. The more electrons flowing through a wire per second, the greater the current. The current of a circuit is measured in amps. An ammeter measures the current. It can be placed at any point in a series circuit to see the flow, but it's also interesting to connect an ammeter and parallel circuit to see how your current flow is being distributed through different paths. Maybe I'll find that about 14 amps per second are being given to the bottom light bulb, while 27 amps per second are being given to the top light bulb. Let's look at real-world circuit examples. Look around your home. Light switches, TV remotes, flashlights, they all use circuits. Think about how they turn on and off. I want to show you guys this photo of the inside of a light bulb. You may think it looks complicated. Parts of it is. We didn't go over everything. But you can see the basic circuit. You can see a light bulb connected to it, the wires, a switch for you to turn it on and off, and then the wires coming back to those batteries. This is an example of a flashlight, but similar things are going on in a TV remote. And the switch in your bedroom is just part of a bigger circuit, parallel circuit, all around your house. In engineering, it's important to be good at problem solving. You don't need wires to think like an engineer, though. Let's imagine we're designing a flashlight. What will we need? Battery, switch, light? Well, we did go over what we needed for a flashlight just last slide, but I want you guys to think of encountering an issue. Engineers have to consider multiple different factors. What if your flashlight doesn't work? Engineers have to test every part to find the problem. Though some people may assume it's the battery immediately, it's important to recognize that it may not be a battery. Maybe the wires are connected all the way. Maybe the bulb isn't working. Or maybe the switch is stuck. These are all weak points in a circuit that could stop electricity from flowing. And we can test them individually to see which one is the issue. We can use a different battery. We can double check the wires. We can test the bulb on a flashlight that is working. And we can play around with the switch. Before I let you guys go, let's do a quick mini quiz. Is a plastic a conductor or an insulator? What kind of circuit goes out if one bulb breaks? And what three things do all simple circuits need? Pause me now as I'm about to answer. Plastic is an insulator. A series circuit goes out if one bulb breaks, and a circuit needs a battery or a power source, a pathway, like wires, and a load, like a light bulb. For this week's activity, I'd like you all to draw a simple circuit at home with labels, labeling the battery, wires, switch, and lights. Label whether it's open or closed, whether it's series or parallel. If you can't draw, write a sentence about how a device at home uses a circuit. Maybe your TV remote, or that flashlight we talked about earlier. Overall, I hope you guys have fun learning about circuits. Thanks for listening.